All right, let's go ahead and get started. We're going to do our best to get through chapter 1 today. Might not quite make it, might run out of gas. You might run out of gas, I don't know. 3-hour lecture is a bit of an issue, but we can do this. Turns out that Wednesday is, after all, our official lecture day. There was a misprint in the scheduling, and that was originally shown as the lab day, but it's now a lecture. So we will be in here every Wednesday for 3 hours, and we'll do this. On Mondays, we will have our lab right next door in 204, whatever. Any questions before we get started? All right. Well, chapter 1 deals with measurements, with atomic structure, with just some of the very basics. We're going to do some very simple calculations. Going to develop an algorithm that will actually be very useful to us throughout all of chemistry. And going to wind up talking about electronic structure of atoms. Matter. It all begins with matter. Matter is defined as any substance that has mass. Remember that mass is different than weight. Weight is the effect of gravity upon mass. Matter is composed of atoms, and atoms are composed of protons, electrons, and neutrons, and a bunch of other things. We are concerned with protons, electrons, and neutrons in this course. Protons and neutrons are localized in the nucleus, and the electrons appear around them in a cloud. We've all seen pictures like this. This is a 1950s version of what an atom was. It's wrong. In spite of Jimmy Neutron and even Big Bang Theory, this is not what it looks like. The things that are wrong is that the nucleus is way too big, and the electrons really aren't in little orbits whizzing around. In fact, the quantum model of the atom looks more like this. We have a little wee tiny nucleus in the middle. This is the element helium. It has 2 protons, 2 neutrons, and 2 electrons in a cloud. Now, this is a cloud. In quantum mechanics, we define a region of space that you could find the electron. That's the electron cloud, and we'll talk more about that later. Atoms are incredibly small. If you could find a real copper penny, that copper penny would contain roughly 28 sextillion copper atoms. Phenomenal number. They're obviously very, very small. Mass of a proton in the nucleus is about 1.67 times 10 to the minus 24 grams. Now, we're going to talk about scientific notation and things like that today, but this is a number that looks like this. We have 3 zeros in front, put our decimal here, and this is 10 to the minus 24. Very, 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 very small mass. When we do exponential notation, remember, we're moving the decimal place over, in this case to the right, 24 places, and that's where the exponent comes from. We'll do that later. The neutron is very similar. It's about the same thing, 1.67 times 10 to the minus 24, and the electron is much, much less. Now, if you stop and think about it, that means that in a given atom, virtually all of the mass in this atom is in this little teeny tiny nucleus. Now in this image, I have made the nucleus 1 pixel. That's as small as I can go. That's even distorted. This is probably a better representation. This is Wrigley Field. And if you look very, very hard, right there on the infield, there's a golf ball. In case you can't see it, there it is. If this was the nucleus, and we set it there on the infield, the electron cloud in something like helium would be the entire stadium. So again, virtually all the mass is in this little tiny nucleus, and all the rest of this is essentially empty space. Remarkable. Elements. If you only have one type of atom in a substance, that's called an element. Every element is identified by a chemical symbol. Quite often the name is based on the English, Ag for helium, for example, but on elements that were isolated and characterized a long, long time ago, Latin or Greek names predominate, and iron is Fe, or ferrium. Elements are organized in what we call the periodic table. Periodic table looks something like this. This one has no numbers, just the letters. This is just to represent, common elements here. Hydrogen, beryllium, magnesium, carbon, helium. You see the symbols more or less match, but there are a whole bunch down here. For example, silver is Ag, lead is Pb, this is mercury, that's lead, I'm sorry, that's not lead, that's tin, whatever. So those are more difficult, and you just kind of have to try to remember them. Now, I'm always asked, gee, do we have to know all these? Well, actually, no. Here's a starter list. Starter list, these are guys that we're going to use a lot in the course. You clearly should know these guys. The rule also is that if we talk about an element or a compound in class, that makes it fair game. So things we talk about in class, your basic starter list, those are the ones you're expected to know. We'll see some examples of exam questions in just a bit. I'm often asked if there's All right, our periodic table is divided up into what are called groups and periods. Groups go from 1 to 8. Now you might count and say, gee, there are more than 8 slots across there. There are actually 18. There are 2 ways to count groups. We're going to use this. These are called actually 1A, 2A, whatever, because they're very useful when it comes to bonding, to identify elements simply by their major groups here. But there are 10 in the middle here that aren't included. These are probably, well, important. Periods go down. We'll see later today that the period actually reflects the energy level of the electrons in that particular atom. You can use the periodic table as a grid, and you can identify things both by group and period. For example, if I ask you what's in group 1, period 4, really the only challenge is remembering which are groups and which are periods. Group 1 here, period 4, we're down to K. K, if you recall from your short list, is potassium. Group 2, period 6. Down here at period 6, we're in group 2A, Ba. Ba is barium. Group 8, period 4. 8 is here, period 4, we're down here, Kr. Kr is krypton. It's not kryptonite, it's not green, it doesn't glow, and it's not toxic to anybody, etc. So remember, groups across, periods down. During every lecture, I try to incorporate slides that have old exam questions. Because everybody always wonders, gee, what's the exam like? So, for example, on this particular area, these are actual old exam questions. Okay? Symbols for silicon, arsenic, bromine, barium, and cobalt. Well, we've seen barium. We know barium is Ba, so we can do a couple of those. Silicon is going to be Si. Arsenic is As. Argon is Ar. Bromine, Br. We've done barium. Cobalt will be Co. And the one that works is this guy. A very simple question. Which of the following has 2 letters in its symbol? Fluorine. Well, fluorine is what we'll call a halogen. It's F. Phosphorus. Potassium was K. Phosphorus is in fact P. Oxygen is O. We'll skip silver. Nitrogen is N. And of course, silver, as we said on the early slide, is Ag. Na stands for natrium. Old nomenclature, that is sodium. Copper, chlorine, cobalt, carbon, and cadmium. Well, copper is a Cu. So we're down to those 3. Chlorine is Cl. So with those 3. Cobalt. Carbon is a C. And cadmium is Cd. Trivial question, which one has only 1 letter? Well, we did iron, we know that's Fe. Pointed out antimony, tin, sodium, phosphorus, of course, is P. Potassium, well, we've done that one. Remember, potassium is not P, potassium is K. Any questions? All right, well, let's go back to our periodic table. How do we line these elements up and make this table out of them? They are organized by what is called their atomic number. The atomic number, typically in a periodic table, one of these guys, is going to be in the upper right-hand corner, sometime in the center. But what this does is this represents or tells you the number of protons in the nucleus of that element. The one thing that defines what an element is the number of protons. Doesn't matter how many neutrons, doesn't matter how many electrons, only the number of protons. If something has 6 protons in its nucleus, it is a carbon. We can combine the protons and the neutrons and the symbol for the element into what's called an atomic symbol. Atomic symbol, you start off with the symbol for whatever element you're dealing with. The mass number is defined as the sum of protons plus neutrons, and we put that as a superscript. And finally, the atomic number, that's the number of protons, goes in as a subscript. It's trivial, but it's a very useful bit of nomenclature. Let's go ahead and work a problem. Here is a little table with data. These are elements. Go ahead and quickly write, while I paste for a moment, the atomic symbols for each of these. Now, what you're doing now is a very important part of this course. There are these slides called in-class problems. In the lecture slide handouts, the problems are there, but not the answers. And a really simple way to do these is to use the mini print and just write the answer in there in very, very small letters. Teaches you to write small, good skill. The more you work problems like this, the better off you will be in this course. All right, hydrogen. Hydrogen, the symbol is H. We have one proton, we have no neutrons. Therefore, our mass number and our atomic number are both 1. Lithium. Lithium has 3 protons in its nucleus. This has 4 neutrons. Therefore, the mass number is 7. Atomic number is 3. Helium. Helium is He. We've seen helium. It has 2 protons and 2 neutrons in its nucleus. Mass number of 4, atomic number of 2. Beryllium. 4 plus 5 is 9. Our symbol is Be. Atomic number is 4. Well, these are the simple ones. Go ahead and do these. In case you don't remember the symbols, oxygen is O, carbon is C, potassium is K, and iodine, of course, is I. Well, oxygen, 8 plus 8 is 16. That's going to be our mass number. Atomic number is 8. Potassium, 19 plus 20 is 39, I believe. K is our symbol. 19 is our atomic number. Carbon, 6 and 6 is 12. That's our mass number. 6 is our atomic number. And iodine. Need a calculator for this one. 53 plus 74. 127 in your head. Very good. Any questions? All right. This is what a test question looks like on this particular area. Mass number of argon is 40. Element is in period group. How many protons, how many neutrons, and write the atomic symbol. Step 1. You have to find argon, don't you? There it is. Argon is over here in group 8. Its 18. Atomic number is 18. That's right. Well, period. Remember, periods go across. So it's in our 3rd period. It's in group 8. If the atomic number is 18, it has 18 protons. If the mass number is 40, that means it must have 22 neutrons. And finally, putting it together in a symbol, it would look like this. Any questions? A neutral element has 12 electrons and a mass number of 24. What is it and where is it? Well, the trick here is to recognize that for an element to be neutral, you must have the same number of protons and neutrons, right? I'm sorry, protons and electrons. Because we have negatives and we have positives. So to be neutral, they have to equal each other. Well, if it has 12 electrons and it's neutral, it must also have 12 protons, which means this is magnesium, atomic number of 12. So this is in our third period. It is in group 2. If its mass number is 24 and it has 12 protons, it also has 12 neutrons, and the symbol would look like this. Any questions?
Period, elements in period 3.
I'm sorry?
The element in period 3, would you please go over period one more time?
Periods. Periods start here, 1 to 7 going down. So period 1, 2, 3, 4, 5, 6, 7, right there, period 3. All right, I would be remiss if I did not have a tutorial to help you go over these things. Now, many of you have already visited the Chemistry Online site and have sent me emails about the tutorials. That's good, because you need to work these. These tutorial questions will form the basis, exactly the basis of your online quizzes. So make sure you do these, make sure you understand how to answer. Here we're going to look at atomic configuration of elements and whatever. So that's this tutorial. Once again, these three here are math review. Make sure that you understand the basics of these guys. And you know, you can just, these are all algorithmic, so you can do these over and over and over again and get a different problem every time you do it. They are imperfect. I wrote them, and mistakes crop up. So be a little forgiving, and I will too. Protons, electrons, and neutrons. We are given tellurium. We are given a mass number of 128, and we are told it has 55 electrons. Fill in the rest of the table. To do these, you need a periodic table. You can actually click and see one, print it, whatever, if you don't happen to have one. But here's our periodic table. We need to find tellurium. And there it is. Down here, atomic number of 52. That means it's going to have 52 protons. If we know the mass number, we can subtract and get the number of neutrons. If we know the number of electrons, compare that with the number of protons, we can figure out the charge. So, for this particular element, atomic number is 52, therefore it has 52 protons. Mass number, we are given 128. If 52 of those are protons, there must be 76 neutrons. Finally, if we have 55 electrons and only 52 protons, we have 3 extra negatives, don't we? Therefore, this is -3. Let's do another one. Bismuth, +3, 127 neutrons. Step 1, find bismuth. It's down here with an atomic number of 83. Take that, fill in your table. If we have 83 protons and our mass number is 127, we subtract to get, or 127 neutrons, we add those to get mass number. If our charge is +3, we must have 3 fewer electrons than we do protons. Therefore, atomic number of 83, 83 protons. If we have 127 neutrons, that means our mass number is 210. Finally, if we're at +3, we have 3 more protons than we do electrons. We have 80. Uranium-235. This is the isotope of uranium that you use when you make bombs. First step, look at our periodic table and find it. Well, I'm sure you're not having much luck because it's not there. That's because uranium sits in this little group called lanthanides and actinides that's at the bottom. We'll explain why that is in just a few minutes. Uranium is right here, though, with an atomic number of 92. All right, given that we have 92 protons in our nucleus, if we're at 235, we simply subtract to get 143 neutrons. And finally, if we have 92 electrons and 92 protons, we are neutral. Any questions? Please work these tutorials. The more you do, the better off you'll be in the course, I promise you. All right, when we were talking about uranium just then, I used the word isotope. What in the world is an isotope? Well, this is carbon. We'll come back to this later in the lecture. Carbon typically has 6 protons, 6 neutrons, mass number of 12. Remember, as long as it has 6 protons, it is a carbon. The atomic symbol for carbon looks like this. Oops. All right. Now, because the number of protons in the nucleus defines what element it is, I could take carbon and I could add another neutron to the nucleus. When I do this, I get a carbon with a mass number of 13. I could do it again. And now I have a mass number of 14. These are isotopes. Isotopes of an element have different mass numbers, but they have the same number of protons in the nucleus, so it's the same element. Now, virtually all elements exist as a mixture of isotopes. Since we're adding mass to these, that means that if you want to weigh out a certain amount of carbon, you need to know an average mass of carbon. The way you do this is to simply calculate the average mass based on the distribution of the isotopes in nature. Calculation is simple, looks something like this. We know that of all the carbon on Earth, 98.89% has a mass number of 12. 1.1% has a mass number of 13. And a teeny, teeny, tiny trace has a 14. Now we can ignore the 14 because it's so small. But if we want to find out the average mass of carbon, what we want to do is simply take the percentage here and convert it into a fraction. If it's 98%, that means it's 0.98. So you're moving your decimal over 2 places, that's all. If we take the fraction and multiply it by the mass for carbon-12, then do the same thing. The fraction, 0.01, 1%, 0.01, times 13, we get a mass of 12.01. If you look at the periodic table for carbon, that is the mass that shows up underneath the symbol in the periodic table. That's the average mass, and that's the mass we use whenever we want to do quantitative calculations. Now we'll do these same calculations 2 or 3 times today even, but just make sure that you understand the concept of isotopes. Oh, here's the periodic table, and you'll see that is 12.01 for carbon. You might wonder how we do this stuff. You know, chemists are amazing. This is what's known as a mass spectrometer. And in order to measure these exact masses and distributions and stuff, what you do is you will take your compound or your element. Down here, you will heat it up so it goes into the gas phase. You will ionize it. The ions are then moved through an electrical grid, which accelerates them, run down this little tube to a magnet. And the magnetic field, it bends the beam. But the amount that the beam bends depends upon the mass. Comes out the other side, and you can analyze based on how much this is bent, what the masses are. Technique is actually amazing. Boron 11 turns out to have an exact mass of 11.009305 and about 80.2%. Boron 10 down here, again, very, very precise way of measuring. Some elements you can get really good masses, some not quite so good. Boron is one of the better ones. Any questions? All right, my periodic tables are colored. Yours is not. The reason that they're colored is to differentiate between classes of elements. Now, the periodic table that you will get on exams will look like these over here. That will not be colored. So you kind of have to remember how to do this on your own. The blues in this periodic table are referred to as metals. These do all the things that metals do. They conduct electricity, you can bend them, you can pound them out, et cetera, et cetera. They're very malleable. They are metals. The yellows, hydrogen, and then these guys on this end here are referred to as nonmetals. Nonmetals basically are insulators. They don't conduct electricity. They're brittle, usually, or gases. Very different in properties, anyway, from metals. And in between metals and nonmetals, it only makes sense that we have semimetals. You have, of course, heard of semiconductors, haven't you? Well, these are the semimetals. They partially conduct electricity, and that's the reason that we have computers and things like that today. Back in the old days, they thought that these guys and these guys, the quote representative elements, were the ones that you found in living things. They were wrong. Actually, they're almost all in living things. But sometimes in books you will see elements referred to as representative. That's what that means. Very old nomenclature. These guys in between. So we have this lump, and then we have these in between. These are called transition metals. Transition metals, again, they're all metals, but their chemical properties represent a transition between the group 3s, group 2s, and the group 3s. This stuff down here, the ones that down at the bottom where we found uranium, this is referred to as the inner transition elements. These actually fit into the chart. They fit after lanthanum and actinium. If we actually took this and stuck it in, our chart would look like this. Here's our inner transitions, again, after lanthanum and actinium. Why do we do that? Well, because this makes it kind of a really long, stupid-looking periodic table. And it's just much more convenient to cut them out, stick them at the bottom. You don't use them for much anyway. And these are the inner transition elements. Yeah?
I was under the impression that those intertransition metals are like radioactive.
Well, actually, lots of these guys are too. Most of these are, in fact, radioactive, as are common isotopes. Radium, for example, is not an intertransition, it's a group 2. It's one of the classic radioactive elements, killed Madame Curie, just like polonium. All right. On the very end of the periodic table, group 8, we have what are known as the inert gases. These are also called noble gases. It's an old term again. Nobility didn't do anything. Inert gases don't react. That's where it came from. Next to it, group 7, we have the halogens. Halogens are a very important group. We're going to use them a lot. Make sure you know them. Fluorine, chlorine, bromine, iodine. You can ignore actinium. These all exist as diatomic elements. So that's F2, Cl2, Br2, I2. We'll talk about that in chapter 2. Group 1 here are referred to as alkali metals. Old nomenclature again, but you'll hear it all the time. And group 2 are alkaline earths. Now, there are lots of different ways that you can represent a periodic table. What we're using here is a very classic representation. There are things that are much more interesting. For example, wind them all up in a circle. Again, you still have to drop these guys out to make it work. Any questions? All right, time for some more questions here. We have phosphorus, atomic number 15, mass number 32. How many neutrons do we have? Well, if the mass number is 32 and 15 of those are protons, we have 17 neutrons. This is bromine 79. What does it have? Once again, please believe me, these are actual exam questions. Well, the atomic number is 35, so we're dealing with either 35 protons or the dreaded none of the above. 35 minus, or 79 minus 35 is 44. No charge is showing here. If this was negative or positive, we would show that as a superscript here. We don't. Therefore, it has 35 protons and 35 electrons. You have to be a university professor to appreciate this. Element administratium has no protons or electrons, has 1 neutron, 75 assistant neutrons, 111 vice neutrons, and 125 assistant vice neutrons, giving it a mass number of 312. What would its symbol be? Well, if it has no protons, it's got to be a 0, doesn't it?
Are we going to cover like all the assist neutrons and vice neutrons and assistant vice neutrons?
Well, have you ever seen the list of administrators at the university? Okay. All right, let's go back to our copper penny. Like I said, we have 28 sextillion atoms. Mass of a proton is this little teeny tiny thing. We're going to show these more properly using scientific notation. Number of atoms in a penny, we would convert this to 2.8 times 10 to the 22nd. Mass of a proton we saw earlier, 1.67 times 10 to the minus 24. Now the process of going from decimal to scientific notation is not difficult. Very simple set of rules. What we're going to do is take a number. We're going to move the decimal point or the implied decimal point so it's after the first non-zero digit. We're going to count to see how many places we had to move this decimal point in order to do this. If we go to the left, our exponent will be positive. If we go to the right, it will be negative. Simple exercise. If we have 950,000, step 1, we don't have a real decimal point, but it's implied to be at the end. We have to move it to the left 5 places. 9.5 is going to be our coefficient. Because we moved it 5 decimal places to the left, our power of 10 is simply 10 to the 5th. Simple exercise. Let's go ahead and do some. Very quickly, take and convert these into scientific notation. Bless you. Our first number, we want to move our decimal point from here over in between the 2 and the 5. That's moving to the right 2 places, so we have a negative exponent of -2, and that's our number. Again, we're ignoring all of these zeros. This next number, here's our real decimal. We have to move it to the left 2 places. +2 is our exponent. show all the numbers. 93 million. We're starting here at the end. We have to move to the left 7 places. So that's 10 to the 7th. It doesn't matter if it's plus or minus. Here we are simply moving in 1, 2, 3, 4 places. And finally, we're starting out here. We have to go 1, 2, 3, 4, 5, 6, so that'll be a minus 6. 2.78 times 10 to the minus 6. Let's do it backwards. Take these and quickly convert them back to decimal notation. Our exponent is 10 squared. That means we have to move to the right 2 places, and this is simply 257. 10 to the minus 7. Going to move our decimal point over this way. We're going to need 6 zeros in front, then our decimal point. 10 to the minus 4, so we need 3 zeros in front, and then our decimal point. Mind you, I'm not counting this 0 that we put in front of the decimal point when I do this. 6.580000 times 10 to the 4th. Well, we're starting here. Going to go 1, 2, 3, 4. Going to have to show all of these numbers, and it looks like that. Why we show those numbers? We'll talk about that in a little while. And finally, 2.78 times 10 to the minus 1. We're just moving it over 1 spot, and that's our number. Any questions? Yes, there is a tutorial. Here we have 83 million or something like that. Convert that into scientific notation.
10 over 6. So 7 over 10?
Yes. Our coefficient is simply 8.3. In order to get there, we have to move this 7 places, and that's 10 to the 7th. .046, we're moving to the right 2 places. Our coefficient is 4.6, and our exponent is going to be minus 2. .1 times 10 to the minus 7. We're going to start here. Going to put 6 zeros in front, then our decimal, and of course 1 extra 0. .6 times 10 to the 7th. Going to start here. We're going to put 6 zeros after that, and it looks like that one. Last one here. We're starting out here. We have to go in 1, 2, 3, 4, 5, 6 places. Our coefficient is 6.1. We went in, what did I say, 6 places. So that's -6. Very nice tutorial, good practice going back and forth. This is an operation that you're going to do a lot. Please make sure that you understand it. Another operation that you're going to do a lot is actually buried up top in the math review. Let's just look at that quickly. These are exponents. All I want you to do here is to give me the resulting exponent of this calculation. Now you have to do two things here. You have to remember, when we multiply exponents, they're going to add. When you divide exponents, they subtract. So that's the first operation you do. The second is you look at the coefficients and you see if that's going to add or subtract another power of 10. So for this problem, multiplication, our exponents will add. We have +5 and -5 giving us a starting point of 0. Now, coefficients. We have 5 times 5, that's 28. Well, 5 times 5 is 25, but you know what I mean. Therefore, we've introduced another power of 10. Final result is 2.87 times 10 to the first, and our coefficient is a 1. Division. Division, we're going to subtract. 1.71 times 10 to the minus 13. 4.11 times 10 to the minus 4. Our operation is going to be 13 minus a minus 4, so that's plus 4, giving us minus 9. Our math operation, 1.7 divided by 4.1 is 0.4, so that's going to subtract another power of 10, isn't it? Our final exponent is minus 10. Now let's do one more. 1.8 times 10 to the 19 divided by 1 times 10 to the minus 10. Well, it's division, so these are going to subtract, aren't they? We have 19 minus a minus 10, giving us 29. 1.8 divided by 1 is still 1.8. Therefore, our result stays at 29, and it looks like this. Any questions? All right, let's take just a 5-minute break here, because 3 hours is a long time. And we'll come back. Oops. And we'll pick up